Hi, my name is Claudio Pinhanez. It's a pleasure to be here. Thank you, Harvard. Thank you, Mane. And also to Professor Alain Amikayan, who introduced us. It's a pleasure to be here. It's my first time in Armenia. I arrived about 10 days ago, 10, 12 days. And I'm leaving 10 hours back to home, which is Brazil. I'm a computer science by training. I have been doing research with AI for 40 years, since AI, it was the beginning, the 80s, when AI was very popular, would take over the world, and people were concerned that all the jobs would be gone. It didn't happen in the 80s. So we are back to that moment right now. And I'm going to try to give you a lot of my perspective in some parts of what's happening now, but particularly around generative AI and the limits and problems and issues that we have in this area. The QR code is my LinkedIn account. I tend to write a little polemic stuff, but that's fine. So just to give a perspective, as I said, I started many years ago. I'm a mathematician by training. Then I went to do master in computer science, PhD at MIT in the 90s. Then I joined IBM Research in 99, 26 years ago. I'm still there. First I was in the US, then I moved to Brazil to open a lab there in 2010. And for the last 5 years I also have been the deputy director of a center that IBM has with the University of São Paulo, an AI center that we do partner work. The work I'm going to talk today is not related to University of São Paulo, although the indigenous work, it is, and I'll talk about it. So, IBM Research is the division of IBM that does research and some development. It's about 3,000 people, a little more or less. We have 15 labs across the world, including one in Brazil, about 100 people in São Paulo and in Rio de Janeiro. We have 2 campuses in Brazil. And the main goal of IBM Research is to produce the technology that will make IBM grow organically. IBM has always to be doing new technology. That's how the company is set up. And we are a big part of creating this new technology. So we have been doing AI for many years. Now also another big and important area of IBM research is quantum computing, which we are trying to create the first usable quantum computing machines. We also have research groups on hybrid cloud and technologies for hybrid cloud, and also security and many other areas. I just want to talk a little, the center for AI that IBM has with the University of São Paulo has about 5 years. It's probably the largest AI center, academic center in Latin America. It has 100 faculty associated. We have about 100 students, between 80 and 100 students receiving scholarships from the center. Many different projects. There is a lot of presence in the web, but it's really a pleasure to be there, especially working with the students and so on. So, but today we are going to talk about generative AI, and just to give you sort of the basic context of what I'm talking. When I say generative AI, I'm talking about text generation with things like ChatGPT, with large and small, and basically transformer-based models. Or, and I will use a lot, I'm not going to use many examples, in this area, but also image generation using this kind of machine. They use different technologies, but in fact have similar problems. People are using also generative AI for time prediction, predicting series. They're using for computer vision, a lot of other stuff. But today, I'm going to talk about text, about the problems that language models have that affect how we can use or should use them. So let's be very honest here, okay? The reality of Gen AI is it produces good outputs for most users, not all of them, most of the time, not all of the time. Okay, that's the reality. And we have been trying to fix these two things for the last 4 or 5 years. A lot of researchers, a ton of thousands and thousands and thousands of papers, and still we cannot fix this. The fact that we still have hallucinations, that we still don't cover minorities, we don't cover special groups of people. I wonder how good models are in doing processing of Armenian language, for instance. Okay, so the reality is this. And a lot of people, and including me, think this cannot be changed. This is something inherent of the technology of transformer-based models. And until we change this technology, we will have to live with these two problems, that they are not always right, they don't work for everybody. So first, most of the talk I'm going to talk about this problem. And normally what people think when we say LLMs don't work most of the time is they think about hallucinations. And I'm going to talk to you, show you some research we have done recently, say, well, not only that, there's another problem. And the other problem is these models are not consistent. They don't always answer the same question with the same answer. And I'm going to give you first a high-level view of that, what I think is the fundamental problem of these models. And then I'm going to show you a study that shows how bad this is for small models like 8 billion parameters. Okay? So, but what are the consequences of this? Well, if they cannot produce most of the time good answers, the whole idea of saying we can't create a model that's trustworthy, which is sort of the holy grail of trustworthy AI. I'm going to get a model, I'm going to train with the right data, I'm going to put something inside it, and that thing is going to be trustworthy. Well, no, it cannot. And we have been beating that with all kinds of research, and still they don't work. We can do jailbreaking quite easily for most models. We can get them to get wrong answers and so on. So instead, what I think we have to move is, instead of thinking that the model is trustworthy, let's think how to use it in a way that's trustworthy. Let's put the controls in the application level. And often that means that we will have to take the output and put a human in the end before it goes to any place. Okay? Because if the model is not trustworthy by itself, I cannot do automation with it. And more people thinking using LLMs for automation is a bad idea. For instance, in Brazil we work with one of the largest banks in Brazil, and the bank realized this the hard way. And this is a bank that runs chatbots since 14. And they said, no LLM ever touches a customer of them directly. Because the chance that the LLM will say the wrong thing or do the wrong thing is high enough and for us to avoid it. So they only do for internal stuff or to support people. And this is a bank that's running, at some point was running the largest traditional chatbot in the world. Remember, doing chatbots with intentions and actions, they were running the largest one in the world with 10,000 intentions. They know what they're doing. And they don't trust these machines. And they're right. They're right. They're good for a lot of stuff. But for automation, only in non-critical situations. Okay? This is why? What's the biggest problem? And I will try to give you my take on the fundamental problems that we need to solve, and possibly we will not be able to solve, to make those things better.
Floating point decisions.
Okay. Well, it's more than that, in my view. But I'm going to talk in a theoretical way. Okay. Why those models are not trustworthy? Because they lack a fundamental property of good models, which is what we call, they are locally continuous. What I mean by that? And I use the word topological here to mean, these are models that take, points in a very high dimensional space and go to another very high dimensional space. So the idea is a continuous, remember, you probably all had calculus 1 or the equivalent in the university. What's a continuous function? You take a little neighborhood around your point, and that thing go entirely into another neighborhood in the output. This is the basic idea of continuous, okay? I know I can be more rigorous than that. I'm a mathematician, okay? But that's the idea. A little, multidimensional sphere here goes inside a known sizable multidimensional function. And this is an essential property if I want to do engineering. If things are not locally stable, if this little ball here can go all over the place here, I have no guarantee about the quality of the system. Because what normally I do to check if a system is behaving like I want? I take my space, I put I sample it, I assume that is locally consistent. So if that sample is well behaved, I say, hey, the whole space is well behaved. And I cannot guarantee that because these guys are not locally, they are not continuous functions. They are not locally stable. And let me give you some examples, but first, there's an important distinction here. Okay, and we are talking about text now, which is when we think about this continuity, are we talking about the mathematical representation of the prompts, which is the embedding space, or our internal, in our brain, representation of the prompts, which is a semantical space. Okay, that's an important question. I'm going to, for this moment, assume we are talking about the space of embedments, but I understand it, of course. So let me try to bring down to this a very simple example. An experiment I did about a year or so ago. About 6 months ago. I was in Japan. I was a little confused about which day I was in, so I went to ChatGPT and asked, what day is today? And for my surprise, of the 10 versions of this question I used, it got 5 wrong. Okay? Of course, when you ask this question about ChatGPT, it runs some agent somewhere because it has to determine right now. But look, it was a Thursday, okay? So that's got the date right, but not the day of the week right. And say, oh, this got confused by time zones. You cannot be wrong with 2 time zones, with 2 days in a time zone, just 1. So if it was a Wednesday, I'd say, yeah, okay, I can give that. But not 2 days. This is the right thing. So answer me the time. So this very stupid question, very simple question. And the problem is most people never do what I did here. So these are, remember the little ball around the dot, right? Those questions are all over here. For us, they are the same. And they should be, in fact, hitting exactly the same point or little variations, but they are all over the place. Okay? So this is the right ways to answer that question with text, and those they are all the way, more than we expected. Okay? So the question that that we have been working on in our lab is how discontinuous are those functions? How much? Trying to quantify this. And today I'm going to talk about one specific case of that. But this is very important because that sets the limits of reliability of these models. So we are in this work, we are doing this work of measuring how consistent. What do you mean consistent? I ask many times the same question. How often you give me the exactly same answer? Okay? One case is you ask 10 times the same question. And, well, we are going to see a lot of time, especially small models, don't answer anything close to what they should. And this is going to show regularly. There is another thing we work, I'm going to talk today, which when we consider similar questions, for us exactly the same question but rephrased. Sort of, they are all in this little ball of sameness. And that I would love to get in the same position. There's a simple way to understand that LLMs are not locally consistent. They are not continuous functions. If they were, prompt engineering would never work. Prompt engineering is basically you do little disturbances in your prompt, which sort of mean exactly the same. And somehow that makes it work. And in fact, prompt engineering is a bug. It's one of the worst things we have. If you cannot get rid of prompt engineering, you'll never be able to have reliable use of LLMs. If a small change produce large changes in the result, that means the system is unstable, by definition. Okay? And we have created a whole culture around prompt engineering about living with these bugs, which is the only way to use these unstable machines right now. So this is sort of the basic understanding, say, this is not a good idea for engineering for a system that I want to use reliably. Okay? Similarly, we'll have later. Okay? Similarly, many of you knows if I want to jailbreak what we call LLMs, make it answer things that it's not supposed to answer, I can insert words or insert spaces and do little variations in the prompt, and somehow I can do what the system was not supposed to do. The most outrageous case is when you just put spaces, more spaces in some key places, and you're able to make the system do what's not supposed to do. This is a problem. This is one more evidence that these systems are critically unstable, to the point they should not be used for anything critically important. So, we also work in this, in measuring fragility. And I have to say, we are appalled by how easy it is to break these models. Okay, to make them, for instance, teach you how to make a bomb, or anthrax, or other stuff. If it's inside their system, so it's easy. Okay, so this leads to a bunch of big research questions in our view, which there's people working, but maybe less than it should. So one is the idea of prompt engineering and model continuity something that's mutually exclusive? Which, I don't know, I believe they are, but maybe tomorrow there's going to be someone publishing a paper saying, no, you just have to do this. But I believe it is, because a lot of people have been trying to fix this and cannot. Okay, the other is, how can we make sure when we train these models that continuity is a big and important big important constraint when they are trained. Okay, and this is a hard one in many ways. Okay, because it's sort of meta level, but probably it's possible. The other is, I have a pre-trained model. Can I force it to be continuous? Can I change the parameters? Can I change the architecture inside so it's continuous? That's a harder one, in my view. And in many ways, the big is, can I pre-train a model to be accurate and continuous at the same time? Okay, so now I'm going to talk about a very special case of this, which is in this paper that we released earlier this year. It's going through a reviewing process. And we focus in a very specific case. Okay? So, but before I go forward, we say, okay, so far I have been talking about continuity, but the title there is non-deterministic. What do you mean by that? And why that happens with those models, okay? When I mean, basically I'm using the word non-deterministic to say, if I ask the same question many times to these models, again, I will get different answers, sometimes very significantly different answers. Okay, it's the classical definition of non-determinism in computer science. Okay, and why we get those? Why those models are non-deterministic, transformer-based models? Well, as I think he was trying to say, there are rounding errors, different hardwares. I mean, 2 months ago, we had a model that a translator which was very good in one machine and terrible in another. The same model, the same libraries. It's just the hardware was different. And terrible meaning would produce endless times the same word, was really bad in this new machine. We had to retrain the model for the machine. What a terrible word to live on if you have to retrain a model for every hardware. Okay, so, but let's go back to attention, all you need paper, 217 paper that created all this wave of AI, okay? So here the classic diagram of the encoder of a transformer, the class diagram of the decoder. How this works? Okay, you put a prompt, you go to the encoder, create an embedding. That embedding changes the decoder. It's inserted inside the decoder to change it. And then you take the embedding of the prompt, push, to the decoder, it gets the probability of the next token, right? Probability of the most likely tokens. Then what do? You run a dice, right? So you run a random number and you choose among all these ones according to the probabilities. What's the next token? Then you put you append to the prompt, encode again, push it again, put it here, run the lottery again, and so on. How to control this random element here that happens at every token? Okay, this is what we call we use a parameter called the temperature. The lower the temperature, more likely that the most likely token is going to be chosen. The higher the temperature, more wild options. So every token creates non-determinism. So if you have an output which is 100 tokens, I mean, that could have 100 possible different ways through a tree of answers. Classical non-determinism. So unless you run with temperature 0, you are living in a non-deterministic world by definition. And even worse, because the choice of the first token determines the choice of the second one, and so on. So you accumulate errors even more. But, okay, so I'm going to run on temperature 0. What happens? Accuracy goes way down for most models. They are not created to be run at temperature 0. They are not good at that place. Okay? So, how bad this is? So what we did is say, let's make this most. We are doing science here, so let's make something that it's very replicable as an experiment. So we took questions from this benchmark for medicine called MediQA, which are from the US exam for physicians. These are questions sort of complicated. Answers are 5 choices. The output of the model has to be 1 letter. Okay? That's what it has to be. Although it often is going to produce a lot of text before saying those letters. You cannot control that. Okay, saying, oh, the right answer is blah, blah, blah. Okay, even if you try. So, for this question, for instance, we asked this model called Medellama, which is a very good model. It's 70% accuracy in average. Very good model for this benchmark. And see, it gets the right question 5 times, 1 wrong 4, 1 1, another one. Well, biomedical Medellama, which is sort of the same class, gets well right. These models are not so good in general, in average, and here we see sometimes they are very strong about the wrong answer. Sometimes they are just all over the place. So this is just an example. So what's amazing is if you do that, it is about, I think, those are 1,200 questions. Okay? So you run 10 times. Okay? And you measure the accuracy. And it's very stable if you take the accuracy across a single one trial. Then you do again, one trial, and so on. Very, very, very stable. But if you look, here we reordered by the number of right questions, right answers, okay? You see there's a whole area where in fact, they are very unstable from trial to trial. So their strategy is not to get the right answer. The strategy is to get the right answer on average. And if you understand how they are trained, you say, that's a great strategy. You don't try to be too focused in one single answer. You try to give chance a chance to get it right. And in average, that leads you to a higher average. So look at this. So see, it's about, one line here, when it's red, means it got wrong for the same question. And see, look, about 40% of the time, that model, which is very good in average, gets it wrong. It's not consistent. Produces, and that's what I say, okay, this is interesting. Let's try to measure it in a more consistent way. So I'm not going into the details how we do this measurement. It's in the paper. But I want to show you some graphs. So these are, the green ones are times when it gets the right answer at least 9 in 10 of the times. Okay? It's consistent, 9 or 10. The same right answer. Here is, it's convict, it's very certain about the wrong answers. It doesn't get, it's not getting the right answer in any way. And here's the time where, well, it's not sure. Okay, for this. And you see that these 4 models for this medical benchmark are very different. Okay? This is run with temperature 0.7, scale 0 to 1. What happens if I run in different temperatures? So what we did is this experiment where we, let me see, no, I want to go here. Okay, here. We took this MediQA, 5 choice, okay, 4 different models that were fine-tuned for this problem. We'd also experimented with the base models that were used for these systems. Okay, these systems were fine-tuned. And also we took a family of models that IBM has called Granite. All of these models are under 8 billion parameters. They're what we say small models, okay? And we run them for temperatures 0.3, 0.7, 1.0. What we saw, so these 3 columns are 0.3, 0.7, 1. Okay, so you see this first model is sort of very good. It's very certain about what's doing. This one, 0.3, okay. When the temperature increases, boom, it gets unreliable. This third model here, no, not good. These models are not good from the start, but look at this. This model, 80% of the time, doesn't know what's answering. It's guessing wildly. Okay? But somehow, guessing wildly, gets still some reasonable. We did with the Granite models sort of same kind of pattern. Okay? Well, when you decrease temperature, it gets better, but sometimes not too much. Still have 10%, 20%, 30%, and so on. Okay? This here, sorry, I made a mistake. This is the base models, which are supposed to be worse. And still, well, not much when you think it this way, which was interesting to see. Granite models, the same thing, same kind of patterns. Increased temperature gets as expected, but even with low temperatures, we are still there. But in fact, one thing we saw, which is very interesting, if you take the average accuracy without considering all these issues of consistency, okay, and here you take the accuracy when the model is sure, what the green stuff, the accuracy around the green stuff, and those things line up quite well for MediQA. So somehow, consistency, when the model is consistent, it's achieving the same levels of accuracy as when it's not. So, hey, it pays to be non-consistent. It doesn't kill you, okay? But more important, here's this blue line here. This is the average percentage of questions that the model is sure. How often the model is consistent. Being right or wrong, but it's sure. And this is for low temperature, T equals 0.3, about 64% only the model is consistent. So basically 1/3 of the time, these models are guessing and are behaving like guessing, and therefore what they are outputting to one person is going to be different from what they are outputting for another one, even at a relatively low temperature, which is 0.3. That we saw across models and so on. But then you might come on, this is medical stuff. So we did used a more general knowledge test called MMLU Redux. Very standard benchmark. Okay? But here we also want to check the difference between small and medium models, medium meaning up to 80 billion parameters. Okay? So this is a 4-choice benchmark. I think we are running 9,000 questions. And again, same patterns. In fact, this test is hard. So we couldn't get much consistency like the one we are getting with MediQA. Okay? For the medium models, we got consistency. For the small models, we didn't. I said, so the problem are small models. We are not sure. What they're saying is we didn't measure it. But we know that large models tend to have much more contamination from benchmarks. So we're not sure if they're answering correctly because they have seen the benchmarks or not. We cannot assure that. We are sure that these small models don't behave well. Okay? So what's the problem? I mean, they are not consistent. Well, if you're using one of those models, for instance, for customer service, one customer asks one question, receives one answer. Another customer answers the same question, gets a different one. Not sure how it's in Armenia. In Brazil, it's illegal. Okay? And in the US, you can sue the company for doing that. So, and we are not talking, it's not a small, we're talking 33% of the time. Okay? For these models. Okay? For the IBM models, we saw the same. These are small models. Okay? And we also saw for the temperature equals 0.3s, again, this correlation between general accuracy and accuracy when they're sure. And we got a similar number in terms of the percentage of sure answers that we are getting from this. Exactly the same question, always restarting the model, all that being taken care of. So the reality of these models is they do not answer consistently the same question at least 1/3 of the times for a reasonable temperature, which is T equals 0.3. In fact, it's a cold temperature for most of this model. So we say, okay, so let's go back and say, remember that I said, trustworthy use of AI. So can my application live with this? Okay, and that's the question. You are a developer, you are a person, just have to ask. But one simple thing you should do is always do this kind of testing of consistency. You're always concerned about hallucinations. Consistency is a different thing. And we have a lot of reasons to believe that these models they use inconsistency as a strategy to achieve higher accuracy. They learn that during training phase. And maybe that can be fixed, okay? If we have time, maybe later I'm going to talk about the Ingenious AI project. What? We have time? So 5 minutes. So that was most of the time. But we have the other problem, that for many users, they are not good enough in a high level, okay? And in our case, we have been also working with this. So again, if you think, oh, I want a model that is inclusive for everyone, that's a dream. That's impossible. I mean, what's true for one group of people isn't true for other people. Here, hey, you're in Armenia. What's true for you, what are true for Turkish people about a very important happening a century ago is different, isn't it? So the idea of a model being inclusive for everyone, it's something, I mean, impossible. But what we have to do again is, okay, we have to do inclusive use. We have to make sure that the use of these models understand their users. And we know how to do that in computer science. It's very simple. We include the users in the process of development. That's how we do inclusive computer science, inclusive programming. We do inclusive development. We do co-development. We do co-design. Or, very common sentence that summarizes this. Okay, imagine these are the users, nothing for us without us. Okay? So if you're developing an AI application for a group of people which the models were not designed for, well, have to design the application around. With them, but always with them. And that's sort of, and we have an extreme case of that. We have been working an extreme case of that because IBM has a program of research for social impact. And we decided to work with indigenous languages in Brazil, processing for them. This is the name of the project. If you want to learn more, this is the Instagram account. We also have a website. We work with the University of São Paulo. We work with a large indigenous organization. I'm going to be very brief. So what's happening in the Amazon is that fast internet has arrived with Starlink. It's true for all rural areas in most of the world. And that has changed completely communications there. And together it came an invasion of dominant languages, in that case of Portuguese language. So we have been working for some time in developing tools based on AI to help people write in their own language, so they can use in social media, they can use it, use it for posts, they can create content, because it's very hard in your own language to write your own language without support of translators, without support of spell checkers and so on. So we have been developing this with AI. I'm not going to talk how. But again, we have to work with the users. So we engaged with a community of people called Baré, which is, I mean, this is the map of Brazil. It's all over there, almost Colombia and Venezuela. We are here. Our lab is here. This is, it's more than crossing Europe, the whole Europe, the distance. Plus, these communities are 5 hours by boat. And we partner with this large indigenous organization. They cover an area bigger than France and Germany together, and has 150,000 people only dispersed there. Okay, we work with them. They helped us select 2 communities, and the way we work with them is we installed 2 digital classrooms in their schools, so we can work with them 4 times a week remotely, without disturbing them too much. And this is how we are doing inclusive development. We had to put these things together. I just want to give you an idea of how complicated and how this place look like. So that's our digital classroom packed. 2 boats, 2 small boats. We live this city nearby. This is called called Rio Negro, Black River. It's the main. 5 hours later, this is a 5-hour ride. Most of the time it's just jungle. And we arrive at this village, about 300 people, to install the digital classroom. What they're saying is, be welcomed. So, handshake at 150 people. So these are tablets, laptops, but also we had to put a solar panel for all this. This is how much work you have to do inclusive development. Okay. So this is the school. But maybe if you go to some villages here in Armenia, are they too different from this? Good question. I mean, in many ways, yes, but not in terms of precarious ways. Anyway, so we are setting up. So this guy has set up 500 points of Starlink all over Amazon. He was amazing. So this is the hotel. This is where we slept. And then we talk. I'm going to go forward. Just one more thing. So we talked with the community, explained what was going to happen. We had already been there. We have done all the protocols that would. And this is sort of the opening of the official opening of the digital room. Wow, this is an old one. Okay, I'm going to stop here. So we're now running 4 weekly workshops with them. About they are writing classes with technology. I mean, this is about 6-7 hours a week. It's a lot of it's an impressive amount of co-design and co-development with the indigenous group, and it's happening really well. Anyway, we hope to expand this next year for 10 more schools if we get funding, if we get support. But anyway, in summary, what I was going to try to say is the systems, these GenAI systems we have, these models, are not inclusive. They are not consistent. They are not right most of the time. So the way you have to solve this right now is to solve it with applications. And to say, yeah, this is more work. Yes, it is. But it's the same thing we did with GPS. GPS signal is totally unreliable, cannot be used for most of stuff. But we are able to create applications that with extra data, it becomes reliable for driving, for people driving with it. You still cannot use GPS for a robotic driving in a city. It's not precise enough. It's never going to be. But we found an application where we changed completely the whole industry of transportation with an unreliable signal like GPS. And that's what we have to do with these models, is to find ways in the applications to fix the problems they have and not expect that they will be fixed by themselves, that they will solve all these problems, which in my view are probably unsolvable with that technology. And what I tried to show you today, some evidence that at least for consistency, we have to be very careful right now. So thank you. If you want.
If you have questions, please raise your hand. We'll bring you a microphone.
First trivial question is, if we want to decrease hallucination for LLMs, why you didn't measure zero temperature?
Because accuracy becomes terrible at zero temperature, in most cases. For these benchmarks, then the problem is accuracy, okay? But, I mean, for some models, in some situations, that may be the solution, okay? But they are just not designed to be run at zero, most of them.
But what is the root reason lost accuracy when we use zero temperature? Because we cannot move the logits on the final layers to the something which will answer to our questions properly. We just follow to the another side when we use zero temperature.
And zero temperature, what happens is that they will if there is a mistake in the first tokens, it can never recover. And that's what the problem is. That's why overall accuracy goes down. And that's why this technology was created with the control of temperature. People who created this found that way back then. And that's why they put that randomizer there, because they found that improves average accuracy. That's the point, average accuracy. But average accuracy is dangerous in some situations. Okay.
To continue the last question, researchers at OpenAI showed that when one particular information in the dataset, in the corpus, is...
I'm not, sorry, can you speak a little louder?
When some info in the corpus appears only once, the chance of hallucination on average bumps up by 20%. So that brings like two issues. First of all, you have to gather a lot of data, but then gathering a lot of data would mean harder like computation, and it would just converge to some mean representing the data. On the other hand, there's the issue whether can you even gather more data. So like how can we deal with that? But like maybe I guess synthetically sampling similar data points to reduce chance of hallucinating, and maybe like mining hard negatives or doing some better attention clipping.
So the question is, there are a lot of people trying to fix these things. My understanding from what I read is you do these things, you create other problems. Okay? I don't think everyone has found a magic bullet to solve. And I believe there are reasons to believe that's fundamentally the model. We have to change the model. And we have, when the transformer appeared in 2017, it solved a long-standing problem in machine learning, a really long-standing problem, which was how to do sequential generation of tokens with a model that can be efficiently trained. Remember, when it appeared, next day we had a seminar in IBM research, people saying, look at this paper. Someone solved it. Well, we need that level of breakthrough, I think, we have to, okay, let's do this in a completely different way. The interesting paradox of this is someone might have already solved this, but with 5,000 papers being issued a day, we may have just lost the solution. So that's one of the problems. We need some sanity in this, some time to read all this, digest all this, because the solution may be out there and it's just buried in this avalanche of work. Okay, that we have out there. But I think we need algorithm change, in my view. I may be wrong, but everyone believes these are serious problems. Okay, which doesn't preclude the use, precludes some use and some direct use. I'm not advocating this technology doesn't work. To work, you have to work in our application to deal with it, to deal with these problems. Who else?
Okay, so basically 2 quick questions regarding this consistency. Have you tested consistency with reasoning models, the small reasoning models, how they change from the base models? And also, did you try any prompting and see how the prompt changes the consistency level?
We did work on similar prompts. And in the case of these benchmarks we did, for instance, we had 5 answers, we changed the order, or we removed one and put none of the above, this kind of, and we found this affected the model. This made it more inconsistent. Okay, so these models, we tested in those ways. What we didn't do is to rephrase the question, probably using another model, because we want to use multiple choice to avoid that kind of error on top of error. So this was a scientific choice. I understand. The real interesting question is the generic rephrasing, which includes the prompts. But for science, for measuring, say, we start with something very simple, very repeatable, very easy to do it. For the reasoning, no, we haven't. I saw a paper that mentioned that hallucination is similar. I mean, reasoning brings its own problems, and on top of that, it increases the cost immensely. Okay, reasoning you generate much more tokens and many more tokens, and this is also a problem for real life applications.
Claudio. Yes, thank you for this great speech. And you said that one of the biggest problems you address is that current language models are not continuous. And this lack of continuity is a bit at odds with my personal experience. Could you please help me realize it? Because when I change my prompt, in terms of when I substitute words by synonyms, or if I add some tiny details, in general, for example, ChatGPT output is kind of the same. But if we change one word, that completely changes the meaning, it diverges. But what do you mean by lack of continuity?
By continuity, I mean if I do a similar prompt, I get a similar answer. Okay? That's my experience is very similar prompts generates very different answers, including all that hocus pocus that prompt engineering does. Imagine that you are a computer science living in an island in the Pacific, blah, 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 all that kind of alchemy. That's alchemy, people. We have to do at least chemistry.
Yes, we try to predefine.
Yeah, you get results, but nothing guarantees that when the model changes, and you never know when the model changes, you're going to still get good results.
But you're talking about continuity of one is the same model, for example, the version of ChatGPT I'm using now, or about how unpredictably a model changes?
Well, first, if the model changes, it's likely it's not going to. But as we saw, and as we tested, I didn't show you, you change the prompt slightly. Imagine that, remember the 5 questions, the 5 answers? You just change the order. And that becomes inconsistent. How come changing the order should change the answer?
Okay, thank you.
It should not. It should not. I mean, of course, it should say now the answer is right as the new one, but it should not. It's the same question. It's exactly the same question, except, so in that sense, for me that's continuity. Okay, things that are for us are absolutely equivalent should lead to a same answer. At least similar answers in the others. Okay? I don't know. There's one there, okay.
Thank you for the presentation. Continuing on the last question, I was thinking you referred to prompt engineering as a bug rather than a feature, right? Kind of like that in Gen AI. What I'm thinking is if we take prompt engineering as a base, wouldn't the functions become more continuous? Like if we decide that we always use prompt engineering, we decide that we use the format, and every time we say, what day is this, give us in the specific format, give me the location, and use that as the base function. In that case, the output would be more or less more continuous.
Well, I think what I just showed you is with 10 times the same question, exactly the same question. 1/3 of the times, it wouldn't give me the same answer. 1/3 of the times, it's not answering the same thing. How can you do engineering with that? Unless you put another layer of control after that. And that's the challenge. That's why I say the use has to fix it. Because the signal, what's coming out, it's not good. It's going to be inconsistent. I mean, we measure for those models public. What I'm telling you, if you are implementing any important system with those systems, measure consistency. Because a lot of times when we think about hallucinations, what we are seeing is inconsistency. And the way to fix the two is different. Okay, because it's consistent, you can say, okay, I will ask many times the same question in some situations, if it's really important. And then you say, okay, if it doesn't answer me the same thing, I will say, I don't know. That's one way to use an inconsistent system. You pay, okay, if it's really important, I'm going to ask many times. If I get different answers, I assume the system does not know, I will say, I cannot know, I don't know. That's one way to fix it. Fix the use, not the system. Okay, and that's the view that I want to give you. Don't trust them for consistency. If it's important for your application, call more times, do checks, do multiple models, do something. If it's in the worst case, say I don't know, I cannot answer you. Okay. Because in fact, the system does not know. It has been trained to go around that topic to find sometimes the right answer. That comes from training. That's the problem. Not sure if I answered, but.
So I have two questions. First, it seems it's not just about transformers, but all autoregressive models, right? When we sample always the next token. But I know that, like, I'm not a specialist, but I know there exists like diffusion, text-to-text models, and so on. Aren't they better at their consistency? And can it be the future where we, instead of just predicting the next token, we just basically transform the whole text with all the transformations?
Well, diffusion also have choices in the middle. So I guess it would be different, but we'll not even try there because first, I've never worked with text diffusion-based text modeling. With imagery, just to understand, just to check whether it's the same answer is a very difficult thing. Okay, so I'm not sure how I would deal with consistency in the case of diffusion-based. But also you have choices there, so it's still non-deterministic there. In the way most of those algorithms work. So I wouldn't be surprised if it's also there. But it's intrinsic of the algorithm. There is a non-deterministic choice. Every token. And you don't even try to I don't know, keep that history to see maybe how much the things have changed and so on. We don't even do that kind of basic analysis of the output, which we could also do to deal with the consistency issue, okay?
Yeah, and the second question is about like your first picture. When you have continuous input, you should have continuous output. But is this actually useful in some practical cases? For example, if I have a prompt that count amount of dots, and I change count amount of dots into count amount of commas in the text, I would like to have a completely different answer just by changing a single token. So to me, it seems that prompt engineering, which maybe is a bad thing in general as it is now, but we cannot like get rid of it as similar as we cannot get rid of how we do computer programming, where we can change like a single line, we get a bug, it crashes. So I think LLMs like cannot be useful without being like some kind of, you change a small thing and it completely changes the output.
Well, most computer programming is deterministic, which helps a lot. So that's the extreme case of consistency. One question, always go to the same one answer, right? No matter how many times you run the same program, you always get. But when I say, it's important to see that locally continuous is an essential property for us to do any kind of engineering. Okay, we don't need to understand the phenomena. But if it's locally consistent, if it's locally continuous, I know that if I do some variation, I can expect the behavior to continue in a reasonable way. Like suppose I'm designing a bridge that goes from here to that wall, and I calculate the beams and all that stuff. What means to be locally continuous in this case? If I say, okay, let me put 5% more in that bridge. If I put a little more material in the beams, it will hold. And that's how we do engineering. Only when we said, okay, let's do a bridge twice the size. Then I have to redo the foundations and then I have to recalculate. But then it's not more local. And then this is not a small ball inside this, a small area. Okay, so we want that kind of property. Otherwise, every time I change a little, I have to recalculate everything. And more important, you cannot do accuracy measuring in a reliable way if you don't have the continuous property. Because when you are doing sampling, okay, you are doing accuracy. Okay, I'm going to do sampling and see if the system is doing well. Plop, 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 plop. You cover the whole space with some dots, so you expect that around them they behave locally continuous. Otherwise, you don't know how well your system is. So the whole basic principle behind testing is locally continuous. Is that the function is locally continuous. Otherwise, I will have to test all possible ways. It's a problem of the classical problem of chaotic functions. A chaotic system cannot be tested. So these systems are chaotic. That's the problem. And prompt engineering is the proof of that. Okay? It's even more. There's some view that their output function is chaotic, but I'm not going to go there. Yes, and you control the time. You decide when we should go for pizza.
Yes, first of all, I want to share my nightmare with you, and that's the reason why I'm here. I'm building AI agents that's giving a person's name, the company he's working, and some other personal information. My agent, basically it is an LLM powered with some tools, for example, Google search tool engine, goes online, scrapes the Google search engine and LinkedIn and so other things, and comes back with a report. Now imagine for the same person, I run my whole agent, and if I run 10 times, 3 times I got criminal records for that person, and that's the other 7 times it didn't appear. I went into details to understand, is it the problem that LLM maybe it is hallucinating? or is inconsistency? Is there an inconsistency in an LLM level? But guess what? The search engine was not deterministic. So querying the same thing on Google, in Google basically, it revealed on the first page. So that is being pumped into the LLM, as a context, reveals different things. So in this level, that's why I'm here. I want to ask a question: is it possible at this level of this transformer architecture that now currently all models are, to solve this problem, or should I wait for some other architecture?
I think the way I would handle this kind of issue is think ways that you can cross-check what you're doing. How can I generated, for instance, the agent's call to some, okay? How can I cross-check what this call that was generated by a system that is not an LLM? So for instance, I'm going to be looking for some key properties, some key checks, some key stuff that will assure, not that it's always right, but it will help me catch some mistakes, for instance. So think that it's a classical security or, safety. You do multiple ways. You don't guarantee that if you try to do the same many times like we do it, it's less stable. And when you're using agents, they introduce a whole level of non-determinism on top, which in your case it's even worse, because what you're querying is not deterministic either. So think this way: how can I not harm my users?
I solved basically putting a disclaimer on my agent.
Well, the disclaimer is dangerous. I would say try to find ways to cross-check what you're doing. And if you're finding discrepancies, you say, I don't know. I cannot help. Okay, I think that's one of the ways of doing it. But it's very hard. That's why it's such a hot topic. But if I would say one thing you should leave today is not everything is hallucination. Sometimes it's inconsistency. And measuring it takes some machine time, but do it. Have an idea of how inconsistent is your basic element before you work too much on accuracy.
If you may, I will ask the last question, and it's about the project that you are doing for these people. So you said that the main challenge is when the fast internet came to what are the main challenges that generative AI is creating for indigenous people?
What are them? Well, the first thing, it doesn't work for them, for their language. Okay? I try to use ChatGPT and say, oh, please translate me these words from Nyingatu, there's a language we work. And it pretends to know the answer. It invents a language, which is even worse, by the way, it's extremely offensive culturally. Okay? If someone says, oh, translate this text to Armenian, okay? And it outputs text in Georgian. How do you feel about that?
No ethics.
You'll be pissed off, and with all reasons. So, I mean, it doesn't work. But you have to be even more basic than this. Search does not work for them. If I try to do search in Google with the words in their language, it brings back stuff from India and from Sanskrit, whatever. And these are Romanic languages, okay? They're written and have a long tradition of, but it just was not trained. Searching, Google search is not inclusive. A lot of these problems we are facing with AI now, they are true for all computer science. Okay? So I want to close. Should we close? Should I close? About a week ago, I went to a talk with Alan Kay. Like some of you may know, the guy who invented object-oriented programming, Turing Award. And he was asked about ethics in AI, and he summarized ethics in computer science with one sentence, which I should have included here, but I forgot. And the way he defined ethics in computer science is software should do no harm nor misleading. Software should do no harm nor misleading. Think about that. Think about a very simple way to think about ethics in AI and computer science and so on. I thought it was brilliant, and I should have included here. I'm going to include in all my last slides from now on. Thank you.
Thank you very much.
Thank you, Harvard. Thank you, Manette. Thank you, Suresh. Thank you all for coming.